This video is going to be called Summer 10, and what we're going to cover in this video is minerals. We have a test coming up this coming Wednesday, and Chapter 1, Chapter 2, and Chapter 3 are going to be on that test. There's going to be 50 multiple choice questions. The information covered in your lab will also be on the test, including except for the metric system. There won't be any metric system questions on the test. That'll be on the lab quiz. And the lab quiz is not till this coming Thursday. Bottom line is, I'm going to cover minerals in this chapter. Chapter 3, and then the next video I'm going to send you is going to be video number Summer 11, and that's going to cover some information about sedimentary rocks, because you need to watch that video so you'll be ready for the sedimentary rocks lab. And the sedimentary rocks lab is going to be due next Tuesday. I'm going to get a box of sedimentary rocks ready for you, and you need to pick it up Sunday after 9 a.m. They're going to be ready Sunday after 9 a.m. Two groups have already returned their box of minerals, but two groups haven't returned their box yet. So please, when you pick up the sedimentary rocks, return the mineral box to me with all the stuff inside. I'd appreciate it. So watch for the next video. That'll be Summer 11. And then I hope you get ready for the lab and also the test, because there'll be a few questions about sedimentary rocks on the test this coming Wednesday. Next thing I'm going to talk about is the chemistry of minerals. And why, you might ask yourself, why is he talking about chemistry? This is geology class. Well, chemistry has a lot to do with minerals. Just as minerals are the building blocks of rocks, atoms are the building blocks of minerals. So a knowledge of chemistry helps us study the earth. My master's degree is in geochemistry, and I use chemistry a lot in, I have used it a lot in my research. So let's go back to some basic. Don't worry, this is not chemistry class. I'm going to walk you through this, and we're going to get this. Just as, okay, so everything's made of atoms. I'm made of atoms. This lazy boy recliner is made of atoms. Those books back there are made of atoms. You're made of atoms. All matter is made of atoms. Atoms are made up of protons, neutrons, and electrons, mostly. There's a whole bunch of other subatomic particles, leptrons and quarks and neutrinos, but we're not going to cover that. Atoms are primarily made of protons, neutrons, and electrons. Back in the 1920s, a great American scientist by the name of Niels Bohr came up with a model of an atom. And this is the basic model of an atom that we still use today. He won the Nobel Prize for this. You probably studied this Bohr model back in high school or any chemistry classes you might have taken at Roane State. Here you can see the Bohr model for an atom. There's a few things that we want to note about this to make it easier on ourselves. An atom, it consists of protons, which are these orange spheres with the pluses in the middle. Neutrons, which are these green spheres with nothing in the middle. And electrons, which are these smaller blue spheres with a negative sign in the middle. In the center of the atom, that's called the nucleus. So in the nucleus of the atom, you have protons and neutrons. The electrons orbit around the nucleus. Now, the important things to remember here are this. Notice how the orange spheres and the green spheres are identical in size. It's written that way on purpose because the mass of a proton is equal to the mass of a neutron. Why are the electrons drawn in with these smaller spheres? Because for all intents and purposes, an electron weighs so little that we can basically consider the mass of an electron to be almost zero. So that means that almost all the mass of an atom, all the mass of the atom is in the nucleus. The other thing you want to notice is that the proton has a positive charge and the electron has a negative charge. And in the subatomic world, opposites attract. In other words, a proton will be attracted to an electron. Remember that for later on. But a proton will repel another proton. Okay, so there's the Bohr model, ladies and gentlemen, right there. Take a good look at it. And now we want to look at the periodic table. This is straight out of your textbook. And you got to kind of look you have to look really carefully at this to understand it. But you can see here that there are 103 different elements in this periodic table. And then you got you got these two, 104 to 118. But all of these in yellow are man-made. So we're not interested in them because they're not found in nature. They're not found in minerals. We're only interested in all of the other elements, not the yellow ones. This first element here in the upper left, represented by capital H, is the element hydrogen. Then helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, etc. So, first thing I want you to pay special attention to, and which is real important if you want to understand chemistry, is that the number in the upper left-hand corner here is the atomic number. Let's go to a real important element here in the city of Oak Ridge. It's a radioactive element, and that's uranium, U. Take a look at uranium. What is the atomic number of uranium? 92. How about oxygen? You're breathing oxygen right now. What's the atomic number of it? 8. Carbon, all living things are made of carbon. Carbon has an atomic number of 6. Okay, we got that now. Now, the first thing you want to remember is the atomic number of an element is equal to the number of protons in the atom. Notice I write protons like this. That's shorthand for protons, so we don't have to write it out. So the atomic number of an element is equal to the number of protons in an atom. Let's work with that now that we understand it. Let's go back to uranium. Uranium has an atomic number of what? 92. How many protons are in a uranium atom? 92. In fact, if an atom has 91 protons, it would be protactinium. If it had 93, it would be neptunium. But all uranium atoms have 92 protons in the nucleus of their atom. Let's do one more before we move onwards and forwards. Look for gold on this periodic table. I'm not going to help you. Look for it yourself and see if you can find gold. Well, I will help you. Gold has an atomic number of what? Well, the way you figure it out is gold. You need to know what symbol is gold. So gold is AU. Try and find AU. There you go. AU. Gold has an atomic number of 79, meaning it has 79 protons in a gold atom. Okay, so we got that part of it right. And now the second thing we want to understand when we look at the periodic table is the atomic mass. What is the atomic mass? Well, let's go back to our trusted periodic table. So we'll go back to uranium again. U. Atomic number is 92. And below that, it tells you how to say the element in English, uranium. And then it has a number underneath that. That number underneath is called the atomic mass. So what's the atomic mass of uranium? Looking at this. Well, we always want to round off the atomic mass to the nearest whole number when we're using the Bohr model. So what's the atomic mass of uranium? 238. 238. So the atomic mass, by the way, is equal to the number of protons in an atom plus the number of neutrons in an atom. NO is neutrons. Therefore, if we want to figure out the number of neutrons in an atom, must be equal to the atomic mass minus the atomic number. See how simple that is? So let's go back to uranium. Uranium, what's the atomic mass? 238 for uranium. What's the atomic number? 92. How many neutrons are in a uranium atom? Excuse me. Well, 238 minus 92, which is equal to what? 146. See if you can figure that out. That's for uranium. So the number of neutrons in a uranium atom is 146. Why is the atomic mass equal to protons plus neutrons? Because the electrons don't weigh anything. They have no weight. They have no mass. Let's do one more and there'll be a question like this on the test, so I want to make sure you can get it. Let's do titanium right here. What's the atomic number of titanium? 22. What's the atomic mass of titanium? 48. How many protons are in the titanium atom? 22. How many neutrons are in a titanium atom? 48 minus 22 is 26, right? We'll do one more here. We'll do potassium here. K, potassium. What's the atomic number of potassium? 19. So there's 19 protons in a potassium atom. How many neutrons are in a potassium? Okay, what's the atomic mass of potassium? 39. So how many neutrons are in a potassium atom? 39 minus 19 is 20. So that's how you read the periodic table. Make sure you can do that for this coming test. There'll be a question or two on that. How do you get out of this? So let me go back to this. Later on, we're going to fiddle around more with this chemistry stuff when we're talking about geologic dating. geologic dating has to do with figuring how old rocks are. Next thing you want to know is what the Earth's crust is made of. Which elements are found in the Earth's crust? Well, notice something quite important here, that the dominant element in the Earth's crust is oxygen, and that's 47% of the Earth's crust. Then we've got silicon, which is 28% of the Earth's crust. So if you add that up, that's 75. So 75% of the Earth's crust is made up of the elements oxygen and silicon. The other 25% is made up of these and some others that are smaller amounts. Next thing that we want to talk about is chemical bonding. So atoms or molecules, which are combinations of atoms, can be held together by chemical bonds. Chemical bonds hold together the atoms or molecules within an atom, within a mineral. Let me see if we get here. So before we go on, we need to know what an ion is. ION. An ion is a charged atom or charged molecule. That means it has a electrical charge, either positive or negative. So something like SO4, which is 4 oxygen atoms bonded to a sulfur atom, will have a -2 charge. Or calcium, Ca, might have a +2 charge. Since this has a negative charge and this is a positive charge, don't you think that they would be attracted to each other since opposites attract? Yes, and you're absolutely right, they would, and they would make this mineral. Okay, so there are 4 kinds of chemical bonds found in minerals. And I'm going to make a list of them here for you. So we have 4 kinds of chemical bonds we need to remember. 4 types of chemical... I hate how it just changes. 4 types of chemical bonds in minerals. We've got ionic bonds, IONIC. Covalent bonds, COVALENT. Metallic bonds, METALLIC. And van der Waals bonds. Why do we call these van der Waals bonds? Because van der Waals is a Dutch name, and Dutch is in the German language family, and W is pronounced V. Anyway, we have ionic, covalent, metallic, and van der Waals bonds. Those are the 4 types of chemical bonds found in minerals. Let's take a look at them one at a time. First, we have ionic bonds. An ionic bond occurs due to, don't forget this, electron transfer. Okay, ionic bonds occur due to electron transfer. And I'll go ahead and write the next one in. Covalence electron sharing, which is a difference. There's a difference between that. So let's take a look at how ionic bonds are formed by electron transfer. Sodium, it's an ion. It's positively charged. It is a +1 charge. Chlorine has a -1 charge. And so you know that opposites attract. And so these will be attracted to one another. To get rid of its negative charge, chlorine could give up an electron and give it to sodium. And then both of them would be without charge. And then you will form the mineral halite. NaCl. That's an example of ionic bonding, where you have a positive charged ion and negative charged ion. One of the ions gives up its electrons, it gives it to the other, neutralizing the, so they both end up having no charge and come together to form a mineral. Ionic bonds involve electron transfer. Ionic bonds are the most important bonds for minerals because they're the most common. And minerals that have ionic bonds are called salts because they will dissolve in water. I'll give you one more example of an ionic bond before we move on. Let's say we have calcium, which is a positive 2 charge. And then we have a molecule SO4. It's called sulfate. And it has a negative 2 charge. How do they both end up being neutralized? Well, since this has 2 extra electrons giving them a negative 2 charge, it can give it up to calcium and neutralize its positive 2 charge. Then it can form a mineral CaSO4. That's an ionic bond. Covalent bonds involve electron sharing. A good example of a covalent bond is, let's see, does anybody remember what Marilyn Monroe's best friend was? And it's before your time. Diamonds. What are diamonds made of? Carbon. And let me see if I can show you how that works. Here you can see different carbon atoms, and they're sharing electrons. See how these blue spheres here are shared between these carbon atoms. So bottom line is, if electrons are shared between different atoms, you have a covalent bond. And covalent bonds are the strongest bonds there are in nature. So they're going to form your hardest minerals. Remember, hardness should go from 1 to 10. All right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Most of you got that right on your lab. But if you didn't, remember hardness is a number between 1 and 10. All of your minerals which are hard, 8, 9, and 10, almost all of them are covalent bonds, have covalent bonds, and involve electron sharing. Okay, the third type of bond is called a metallic bond. And all of your minerals that have a metallic luster, most of you did good on the luster part of the lab. If metallic luster, by the way, means that it's opaque, light will not pass through it. Usually it's shiny. If it's not shiny, at least if you rub it against a white streak plate, it'll give you a dark color. And you cannot break it apart with your fingers. Metals are hard. So a metallic bond in a mineral involves electron movement. Okay, so going back to metallic bonds involve electron movement. So electrons can move between atoms. So a stream of electrons moves between atoms in a metallic mineral. And what is a stream of electrons but electricity? And so we call metallic minerals are electrical conductors. They allow for electricity to move through them. All metals conduct electricity. So electrical conductivity is associated with metallic bonds. Van der Waals bonds are an electrostatic bond. Electrostatic, meaning they are very weak bonds. Best example I can give you is if you walk on a carpet and you touch your friend, what's going to happen? There's going to be a very light electrical charge. Without getting into the detailed chemistry, because this is just an introductory geology class, just remember Van der Waals bonds are the weakest bonds in minerals, and they're found with the softest minerals, such as talc and gypsum. So those are your 4 types of chemical bonds. All minerals can be divided into 2 main groups. Minerals can be silicate minerals, or they can be non-silicate minerals. All minerals are divided into, classified as either silicates or non-silicates. Silicate minerals contain silica tetrahedron. Non-silicate minerals do not have any silica tetrahedron. Now, what is this silica tetrahedron? Well, chemically, it's 1 silicon atom bonded to 4 oxygen atoms. It's a molecule, SiO4. And if you look at this pyramid-like structure, that's how you can visualize a silica tetrahedron. You got 4 corners on this tetrahedron, 4 points, and on each point you have an oxygen atom, and in the center you have the smaller silicon atom. Or you could look at it like this picture right here, where these 4 pink spheres. These 4 big pink spheres are oxygen atoms, and the little silicon atom is in the center. This shows you the little silicon atom in the center. So non-silicate minerals do not have these silica oxygen tetrahedron. Let's take a look at some mineral chemical formula and see if we can pick out the silicate minerals and the non-silicate minerals. Real simple, ladies and gentlemen. Okay, here's my hint here. Looking at the chemical formula of a mineral, if it has Si, which is silicon in it, and O in it, then it's a silicate mineral. If it does not have silicon and oxygen in it, it's a non-silicate mineral. So let's see if we can do this here. Diamonds and graphite, those are 2 minerals. Are they silicate minerals? No, there's no Si and there's no O. How about Fe2O3? No, there's no Si. There's oxygen in it, but there's no silicon. This is a non-silicate mineral. Hematite is a non-silicate mineral. How about calcite, which fizzed with acid? CaCO3. Is that a silicate mineral? No, there's oxygen in it, but there's no silicon. In fact, this chart doesn't show you any silicate minerals. So let me go to the... Here's some examples of silicate minerals. Olivine, it has Si and O in it, so it is a silicate mineral. How about garnet? You had garnet in your minerals. Does it have Si and O in it? Yes. So garnet is a silicate mineral. Quartz. Is quartz a silicate mineral? Yes. It has Si and O in it. Plagioclase feldspar. Does it have Si and O in it? Yes. Therefore, it's a silicate mineral. I'll close off this video by saying this. 90% of the minerals in the Earth's crust are silicate minerals. Only 10% are non-silicate minerals. Remember that. And it's easy to remember if you think the composition of the Earth's crust is primarily oxygen and silicon. In the next video, I'll talk about sedimentary rocks. And the video after that, I will finish off this chapter. And that'll be it for this week.